All right, Elon Musk has finally revealed his reasons for pouring in excessive resources into his Mars mission. Musk is not...
Mars's atmosphere is primarily carbon dioxide, which shows you how long, it's been there for 4 billion years, shows you how long.
Humanity has always looked to the stars with curiosity, awe, and ambition. Among the countless celestial bodies, one world stands out as both a challenge and an opportunity: Mars. For decades, it remained a distant dream, a planet visible through telescopes, yet untouchable. Today, that dream is closer than ever. Elon Musk and SpaceX have reignited the imagination of millions, promising a future where humans do not just observe Mars, but live there. With the development of Starship, the most powerful spacecraft ever built, and the Starlink network, designed to blanket Earth and eventually interplanetary space with connectivity, Musk's vision begins to take form. If exploring the final frontier excites you, if the audacity of interplanetary travel captures your imagination, make sure to subscribe now, because this journey is about humanity stepping beyond Earth, redefining its limits, and reaching for the stars. Now let's delve into the bold, unprecedented plan to make Mars humanity's second home. Elon Musk's vision for Mars colonization. Musk's Mars vision is rooted in both urgency and scale. He proposes that humanity must become a multi-planetary species to ensure long-term survival. Mars is not simply a destination, it is a safeguard against existential threats, including nuclear war, asteroid impacts, and ecological collapse. The plan involves transporting large numbers of humans to Mars efficiently, creating sustainable habitats that leverage local resources, establishing a self-sufficient colony capable of growing food, producing energy, and manufacturing necessary tools. Gradually scaling up from a small settlement to a thriving Martian civilization, Musk envisions fleets of SpaceX starships, transporting hundreds of colonists per mission. The ultimate goal is a population capable of self-governance, independent of Earth, transforming Mars from a barren desert into a functional, sustainable world. This vision is audacious, but the meticulous planning behind it reveals a blend of engineering pragmatism and visionary ambition that has captivated engineers, scientists, and dreamers worldwide. SpaceX Starship development. The Starship spacecraft is central to Musk's Mars plan. Designed to be fully reusable, Starship combines enormous payload capacity with interplanetary endurance. Key technical features include a height of 120 meters when paired with the Super Heavy booster payload capacity, exceeding 100 tons per launch, stainless steel construction for heat resistance during atmospheric entry, methane-fueled engines designed to be refueled on Mars using in-situ resources. SpaceX has approached Starship development iteratively, using rapid prototyping and testing, including high-altitude test flights and booster integration. Each success and failure informs the next step, accelerating progress while managing risk. This approach reflects a philosophy that blends ambition with pragmatism. Speed is essential when building a vehicle, capable of carrying hundreds of humans across interplanetary space. Challenges of interplanetary travel. Transporting humans to Mars is not merely a question of rockets. Space travel involves extreme environmental, psychological, and logistical challenges. Some of the most pressing obstacles include radiation exposure. Outside Earth's magnetosphere, cosmic rays and solar radiation can threaten health. Solutions include shielding materials, underground habitats, and possibly electromagnetic deflectors. Microgravity effects. Long periods in zero or low gravity affect bone density, muscle strength, and cardiovascular systems. Countermeasures such as exercise protocols and artificial gravity designs are under consideration. Life support systems, oxygen generation, water recycling, and waste management must function reliably for extended durations without resupply. Psychological stress. Isolation, confinement, and distance from Earth can impact mental health. Social structures, recreation, and communication are critical for sustaining morale. Overcoming these challenges requires innovative engineering, careful planning, and resilient human behavior, ensuring that the Mars colony is viable from day one. Mars colonization logistics. Building a self-sufficient settlement demands resource utilization and infrastructure development. Mars offers key advantages, despite its harsh environment. Water ice for drinking, oxygen production, and fuel generation carbon dioxide in the atmosphere for fuel synthesis and habitat pressurization. Regolith for construction material and radiation shielding. Musk's approach includes establishing initial small colonies which grow in stages: unmanned missions delivering habitats, equipment and supplies, crewed missions to assemble and expand infrastructure, development of agriculture, energy systems, and fuel production, gradual population growth toward a self-sufficient Martian city. This staged strategy balances risk and progress, turning the Martian dream into a pragmatic roadmap. The role of Starlink in interplanetary communications. Deep space exploration requires reliable communication networks, and Starlink is central to this plan. While currently Earth-focused, the constellation of thousands of low Earth orbit satellites provides a proof of concept for interplanetary communication. Starlink's potential contributions include real-time communication between Mars and Earth via relay satellites, data transmission for scientific experiments, resource monitoring, and navigation internet connectivity for colonists, enabling education, entertainment, and psychological well-being. Integration with autonomous systems, supporting rovers, drones, and habitat maintenance. By extending the Starlink concept to Mars orbit, SpaceX could create a continuous, high-speed communication link, ensuring that humans remain connected across tens of millions of kilometers. Mars transportation infrastructure. Starship is the first step, but establishing logistics on Mars is equally critical. Musk's plan includes landing sites near water ice and sunlight for energy generation, construction of durable habitats capable of withstanding dust storms and temperature extremes, fuel production facilities using CO2 and water ice to synthesize methane and oxygen, enabling return trips to Earth, autonomous construction using 3D printing and robotics to minimize human risk. This infrastructure ensures that Mars is not merely a temporary outpost, but a functional, sustainable settlement capable of growth and expansion. Energy and sustainability. Energy independence on Mars is essential. Proposed solutions include solar arrays optimized for Martian sunlight and dust conditions, nuclear reactors to provide continuous power during dust storms or night periods, energy storage systems using advanced batteries or fuel cells, resource recycling to minimize waste and dependence on Earth resupply. Sustainability extends to food production, where hydroponics and controlled environment agriculture allow colonists to grow crops despite the planet's thin atmosphere and low temperatures. Human factors and social organization. A Martian colony must address the human dimension. Beyond physical survival, colonists require psychological well-being and social cohesion. Governance structures adapted to isolated environments, education, cultural activities, and recreation to maintain morale redundancy in roles and cross-training to handle emergencies. Musk envisions a pioneering spirit where each individual contributes to both survival and the long-term growth of Martian society, creating a culture of resilience and innovation. Phased Mars settlement. The settlement plan is incremental and adaptable. Initial small crew establishing habitats and testing life support systems. Expansion through repeated Starship missions, growing population, and infrastructure. Integration of robotics and autonomous systems to reduce risk development of a semi-autonomous city with local governance and manufacturing. This phased approach balances risk, cost, and technological feasibility, making the dream of Mars colonization tangible within decades. Scientific and exploration opportunities. Mars offers unparalleled opportunities for research, studying planetary geology and climate evolution, searching for signs of past microbial life, understanding the effects of low gravity and radiation on humans, testing technologies for future interstellar missions. The colony becomes not only a foothold for humanity, but also a research hub, generating knowledge critical for long-term space exploration and survival beyond Earth. Starlink and deep space connectivity. Starlink's low Earth orbit constellation demonstrates the potential of high-speed, low-latency communication. Extending this network to Mars involves deploying satellites in Martian orbit, creating a planetary communication grid capable of connecting Earth, orbiting satellites and surface colonies. This network allows continuous data transmission between Mars and Earth, support for scientific experiments and remote monitoring, coordination of autonomous systems and robotic infrastructure, real-time communication for colonists, reducing isolation and maintaining morale. The Starlink approach demonstrates how scalable satellite constellations can provide connectivity across planetary distances, turning Mars into an integrated, connected outpost of humanity. Mars orbital infrastructure. To support both communication and logistics, Mars requires orbital infrastructure. Proposed components include relay satellites forming a mesh network for uninterrupted signal coverage, orbital refueling stations for interplanetary transport vehicles, surveillance and monitoring satellites for weather, dust storms, and surface changes, scientific observation satellites to gather real-time environmental data. These elements ensure that Mars is not only habitable, but technologically integrated, capable of supporting a sustainable, connected civilization. Energy systems on Mars. Reliable energy is central to survival and expansion. Mars' energy strategy includes solar farms designed to operate efficiently under Martian dust conditions, compact nuclear reactors to provide continuous power during low sunlight periods, advanced energy storage systems to buffer fluctuations and maintain reliability, distributed microgrids connecting habitats, greenhouses, and industrial facilities. This combination of renewable and nuclear energy ensures that Martian colonies can function autonomously from Earth for extended periods. Transportation and logistics networks. Efficient logistics are critical for Mars colonization. Musk's plan includes Starship fleets ferrying humans, cargo and equipment, autonomous rovers and drones constructing habitats and infrastructure fuel, production facilities converting water ice and CO2 into methane and oxygen for return journeys, surface transport systems linking landing sites, habitats, and resource locations. This infrastructure transforms Mars into a functional ecosystem, capable of supporting population growth, research, and industry. Terraforming prospects and long-term sustainability. Mars colonization also opens discussions of planetary engineering. While full-scale terraforming is centuries away, initial strategies include establishing controlled biospheres and pressurized habitats, incremental warming of local areas using energy-intensive methods, generating oxygen and sustainable life support cycles, cultivating agriculture capable of supporting growing populations. These steps lay the foundation for long-term sustainability, ensuring that future generations thrive on Mars. Robotics and autonomous systems. Robotic technology plays a central role in colonization. Autonomous construction systems build habitats before human arrival. Drones survey terrain, monitor weather, and assist in logistics. AI-driven systems manage life support, energy, and resource allocation. Integration of robotics reduces risk, increases efficiency, and ensures continuous operation, even under harsh environmental conditions. Scientific opportunities on Mars. Mars offers unparalleled avenues for research, and if you want to witness humanity pushing the limits of possibility, subscribe now. Join us as we track Starship launches, explore Mars colonization strategies, and follow the evolution of interplanetary communication networks. The universe is vast, the challenge immense, and the adventure has only just begun. Humanity's journey to Mars continues, connected, daring, and unstoppable.